Hello, everyone, and welcome to our online seminar series for Inspire at the University of Saskatchewan. And I would like to start by acknowledging that as we gather virtually today, we acknowledge that most of us at the University of Saskatchewan at the CLS are on Treaty 6 territory in the homeland of the Métis. We pay our respect to the First Nations and Métis ancestors of this place, and we reaffirm our relationship with one another. So a little bit about this seminar series. This is something that Ardalyn and I came up with. We wanted to put together a seminar series to connect people with Inspire or within Inspire with the greater synchrotron community, whether that's at the CLS or international users. And so this is going to be a seminar series that will be run on alternating Wednesdays. So today is the first Wednesday that we're dealing with. It'll be from 1:30 to 2:30 in Zoom. And if you have suggestions for speakers, whether that's internal to Saskatoon, University of Saskatchewan CLS, or external, so it could be international users, anything that involves synchrotron-related innovation, applications, research activities, or professional development, we're interested and we would like to hear suggestions. So please send those our way if you have them. A little bit of housekeeping before we get started. So for everyone who's here, if you could keep your video and mic off during the presentation, this will reduce bandwidth and distractions. Be aware that we are recording this. And if you have tech issues, please message either Ardalyn or Lenore. And if you have questions for the speaker today, you're welcome to put them in the chat, or you can hold them onto them when we get to the Q&A session at the end. So at this point, I would like to introduce Dr. Alexander Moews. He is a professor in the Department of Physics and Engineering Physics at the University of Saskatchewan. He held a Canadian Research Chair in Materials Science with synchrotron radiation. And today he's going to talk to us about direct measurements of energy levels in next generation nitride phosphors for lighting applications. So whenever you're ready.
Thank you very much. I will share my screen. So thank you very much for this invitation. I'm excited, and I will show you later that I have also a number of students that participate and are funded through Inspire. So I'm a strong advocate of this program. So what I'm going to talk about is, first I'll give you a brief outline here, start with some acknowledgements, give you a few slides of motivation, and then also some applications for LEDs and to show that there's a wide variety of requirements for light emitting diodes. Then I will very briefly talk about the samples, and this is one thing that I don't try to get across today. What are exactly the samples? What are the structures? If you have questions about this, feel free to ask. I have slides, but I don't show this because I want to focus on the science. Also, I will not talk much about the techniques that we are using, but if you have questions about that, either ask me, or I'm actually happy also to give another talk, maybe an Inspire, about these techniques. So I keep it about the science today. Next thing I will talk about the problem, meaning which problem are we tackling? And this problem is, how do we determine the 5D energy levels in europium-2+. And then, of course, I will tell you the results and how we tackle this problem. And then I have added also 3 slides on 2 recent publications on germanium phosphor nitride, a new nitridophosphate. And then I have a 1-slide summary. So start with the acknowledgements. So our person without nothing works at Rijks is Tiet Boyko, former graduate from our group. He's the beamline scientist at the Rijks beamline. The calculations and experiments were all done by people that have now left the group, except for my postdoc, Tristan. And the reason for that is that I try not to steal any thunder of my students of stuff that they are working on right now. So Thomas, who is now working in Montreal in industry, was the main body of work. Then Ruhul, I show also a few of his results, who finished last year. And as I said, Tristan is involved in the outlook and the what's called ADF calculations. I just want to shrink here one little picture. Okay, I think this works. For the calculations, we used Westgrid Compute Canada resources, and for the synthesis, the person that made the sample is a former PhD student from a friend and collaborator at LMU in Munich, Schnick, Wolfgang Schnick. His name is Philipp Strobel. He also graduated. I was on his committee, and he came actually to visit our group for about 2 months in Saskatchewan to work with us. Let's start with some motivation. Why is it that it's advantageous to do research in light-emitting diodes? So there is obviously this curve that we are all aware of, that we are pretty bad in being responsible as humans for an exponential energy growth. You see here the global energy consumption. And there are 3 components of this: electric, transportation, and heating. And the electric part is, of course, where the LED come into play. And the electric part, I just wanted to mention this, we're talking about possibly 20% of the world's energy consumption, and that part is electricity. So there can be potentially great benefits to finding more efficient light-emitting diodes. So in the US, it's always difficult on these websites to find numbers for Canada alone. So that's why I focus on the US. In the US alone, lighting accounts for 6% of the total energy and 15% of the electric energy. It's a little bit higher for cities. And the Department of Energy has put out the goal that in 20 years, they want to, by replacing incandescent light bulbs with modern LEDs, want to save substantially great amounts of energy, and these energy savings amount to about $630 billion in avoided energy costs. So in other words, this is a huge market, LEDs, and this has huge benefits in terms of the savings in energy and in cost. And this is, by the way, entirely achieved in lighting applications for light-emitting diodes. How does a diode work, or light-emitting diode work? So it turns out that the human eye has 3 different kinds of cells. They are for the 3 different wavelength ranges, blue, green, and red. And now if you have a phosphor, or if you have 3 phosphors that cater to these 3 different wavelengths or energies, and you know how to stimulate also the brightness, then you basically have the eye perceive the light emitted from these 3 sources as white light. And this is what you ideally want to do, unless you have special lighting applications. This is what you want to achieve. So you see here, there basically are 3 different materials. In this case, there is a starting indium gallium nitride LED that stimulates the other 2 sources, and output is then in the 3 wavelength would be perceived as white light. I mentioned here also that the Nobel Prize in Physics was in 2014 given for the invention of the blue LED. What is relatively amazing to me when I started this is how fast in this area the time from discovery of the material and studying of the material to the product that is a light bulb that you can say buy at Home Depot or Costco or wherever you purchase this, how short this time is compared to other things that took probably 20 years or more for the electron microscope, which everybody has today, every lab. But in this case, it's only about 4 years. So it's a very fast-paced field. So I give you now just the point of the next 3 slides is only the requirements on what kind of LED parameters you would like to have can be quite different. So for example, here is a material, the materials are always complex nitrides. Here in the top, you see this, that shouldn't bother us too much. So one application is in Audi, the front and rear indicator lights are from a material that we have researched. And the company that actually puts this into the what I would call commercial product is Lumileds, a company in Germany, in Aachen, that we work with. And so in this case, you would have a light which has to have high stability of different over a large temperature range, but you don't want necessarily white light. As you know, the indicator lights have to be a certain color. That has to means that it has to have stable color and also high stability with, say, different temperatures and so forth. So the second application is what you all love and care for. This is your cell phone, the flash bulb. And so this is another application where you want to have a short flash. And again, here the case would be you want to have a very wide sun-like spectrum generated so that the pictures taken with a flash on your cell phone look great, and you don't look like you are hungover or you're green in your face or whatnot. So it is amazing what I learned. Also, another thing, how ingrained in the human vision the spectrum of sunlight is. Slightest deviations in photographs from lighting that deviates from the light of the sun lead to drastic effects on how people perceive the image that they are looking at. And this is captured by what's called the color rendering index, CRI, that tells you basically how similar the spectrum is to the spectrum of the sun, the black body radiation. There is a special application also, for example, to show something different in horticultural lighting, where you have here shown three different, a blue LED, another one, and SLA, a topic that, or a material that we also studied. And you cater now with three different wavelength bands. You cater to different photosensitive species in the plant. So this is a very different, say from the light or from the flashlight in the phone, different application. Okay, the samples, I only want to say briefly one thing. I will largely present, excluding the germanium phosphor nitride is a different topic, 4 different samples. And they are, I will show one general graph about them. They are nitride phosphors and they are doped with europium. Europium 2+ is the emitter in these materials. And so why did I choose these materials? The point about these materials is that they have structurally, they are very similar, but they have quite different luminescence properties. So the idea is that through the choosing of the lattice, of the host lattice, you trigger or tailor or alter the luminescence properties of the europium 2+ emitter. That's always the principle. So you want to, of course, be able to tailor the light output in various parameters, and color rendering index and efficiency and wavelength and so forth. So what are these materials? They are all nitrides, except for one oxygen nitride. And they have always in common that they have these tetragonal figures here, where they have corner sharing nitrogen on each corner. And then these tetrahedra are put together, and the heavier or larger atoms are put in between these spaces. So now this is shown here for SLA, one of the more famous materials. And now the bottom line is the structure here remains the same, with except for small modifications of the distances. And you can now switch, say, strontium with barium or calcium, aluminum with magnesium, lithium with silicon, and the nitrogen always remains the same. So we don't go into the details. I have structural pictures about exactly those, but the point is you have a similar class of materials, you only change elements, and that allows one to tailor or cater to different luminescence properties. Let's zoom in now on the problem. So here, luminescence is what the visible light is produced by luminescence, and the transition is in europium, the 5D electron decays into a 4F level. Okay, so 5D, as shown here in the right graph, 5D goes to 4F. This is just an intrinsic transition in the europium 2+ dopant. Now, because the dopant is put into a host lattice, it turns out that these states are what's called intra-gap. So there is a band gap between the valence band and the conduction band. And it turns out that these additional states from the dopant that are responsible for the visible light output, they are residing in the band gap. And when you know now that europium 2+ has no 5D electrons in the ground state, so it has 5D0, then you will see immediately that it will be difficult, because it basically requires a 2-photon experiment. It will be difficult to probe the exact position of the 5D element, of the 5D orbitals. Okay, so the question is, how can you probe in the ground state the the 5D levels. Because the luminescence, the initial luminescence state, which is 5D1, is an excited state. So again, in order to tailor luminescence, one needs to, of course, know where the 5D are, because 5D to 4F is the transition. If you change the 5D energy position, you change, among other things, the wavelength right away. There is a problem I should also mention about calculating. When you deal with these things and try to calculate this, you deal with two open shells. You have the 4F7 shell and you have the 5D1 4F6 shell. And this is difficult because it leads to very large matrices. So these are complicated calculations. Okay, now the whole point about 5D levels is, unlike the 4F, which are very localized and basically almost it does not matter in which host matrix you put them in, the 4F levels are always in the same energy position, roughly spoken. The 5D are very susceptible and sensitive to the host lattice. And this is through two effects. I've shown them here. It matters how strong the bonding is of the nitrogen atoms. This is basically the nephelogesitic effect. And then you see here, this would be the free ion, the 5D24F. Now you have, depending on the ligands, you have the first effect. And then, of course, also like any energy orbital that you put into an electric or magnetic field, they are splitting. And it turns out that depending on the crystal field, in other words, depending on the host lattice, you will have different crystal field splitting. And this crystal field splitting, of course, is what's responsible for shifting the wavelength. Why is this desirable? Again, because you want to be able to tailor your emission, your visible emission, in order, for example, to get sunlight, a sun-like spectrum output, and in order to have a good color rendering index. Oh, by the way, here is shown, I don't think it's so interesting, here is shown, so for an LED, you have the three contributions. The green curve here will be the total emission, and then here you have the black body radiation of the sun, or for two different temperatures in red and in blue. And basically the goal is to emulate with this triple emission here from the LED. You want to emulate whatever kind of spectrum you need to have for either the car or for a flash or whatever it is. Okay, so the question is again, how do we measure the 5D europium energy levels? And the obvious question is, this is not something we invented or by any means. The question is, people do this since a long time. And I wanted to quickly tell you, how do people do this? So it is shown here on the right side that the quenching of luminescence is an important parameter of a functionality of a light-emitting diode. So what happens is you see the temperature displayed, and on the vertical axis you see, it's only an emulation here, you see the luminescence output and intensity. So now the point is, when you increase the temperature, the luminescence starts to go down. This is because of Doornbos has defined this process. This is believed to be due to the promotion of 5D electrons to the nearby conduction band. And it is clear when you have 5D24F as the emission process, then it's not advantageous if you promote 5D electrons, which are your light producing electrons, when you reduce the amount by promoting them through thermal excitation to the conduction band. So this is called quenching. Okay, it's a simple function here, which depends on the temperature, on the Boltzmann constant, and on delta E. And delta E is now the distance here, the distance from the 5D to the conduction band. So now clearly when you measure, this were emulated curves in origin with this model, but bottom line is when you now measure the thermal quenching, the decay of the luminescence with temperature, then you can use a fit to derive delta E. This was how delta E, the distance from 5D to conduction band, how this was up to date evaluated. Now, there is one disadvantage, other than that it's an indirect method. One other disadvantage is most samples, especially when they are new and hot and synthesized the first time, they are not in a very pure phase. They have impurities, they have defects, and all these imperfections lead typically to a reduction because electrons that travel in the material are lost. And therefore, you can never be sure when you have now a loss in luminescence because electrons are trapped by imperfections, then you can never be sure that this is really giving you the true delta E. It could in fact be that the sample is so imperfect that lots of electrons are captured by imperfections or trapped by imperfections, and that leads to a reduction in luminescence as well. The method that I'm going to show you is independent of the level of impurities in the material. Okay, I quickly in one slide wanted to tell you what X-ray absorption and X-ray emission spectroscopy probe. So here you see the calculation for band structure. Here is the valence band. Here's the conduction band with a lot of density of states. And then hopefully you know already, I think when you have been through Inspire presentations, you basically have here the absorption spectrum, roughly spoken. You just take the projected density, you sum them up in a horizontal direction. You flip this now by this spectrum here, which is just the sum integrated always in this direction, crystal momentum. And you flip this clockwise and you get the absorption spectrum. So I think most of you will know that when you now come in, and here you see the nitrogen 1s in this case, probing the conduction band. So what happens here upon the careful selection of your incoming energy, you take a nitrogen 1s electron and you promote it to the conduction band, and not a surprise, X-ray absorption spectroscopy in this case probes the unoccupied partial density of states. Now we have, of course, an excited system with the additional electron here and the hole here in the 1s shell. And like any good physics system, this shall decay. And now, of course, if the same electron would go down, this would only give rise to elastic scattering. Energy in is same as energy out. So that's not interesting, at least to us. And so when we take the same calculation, roughly spoken for a moment, and now the point is, we don't want to look at the same one going down. That's the same energy. We want to look at the valence band where the electrons are sitting. The valence band are the occupied density of states. And what happens now is that the valence band electron come down, refill this hole, and if, among many other things, predominantly Auger electrons, you have the energy released in terms of a photon. This is called an emission photon typically. And you can analyze this energy of these photons, and then you have the density of distributions in the valence band. Okay, so what you see, absorption probes the conduction band or unoccupied states, and emission probes the occupied states or valence band. If you have both together, you immediately have the band gap. Then you put this together, so you see always here the projected density of spectra, and this is now for 1K, is calculated and measured for the gamma germanium nitride. You see here the calculations, emission and emission. Emission and absorption, and here you see on top the measured spectra. What I have not told you, and I will spend 30 seconds on this, two things are important for optical transitions because the photon has momentum, and momentum is always conserved in physics in a closed system. So because of that, you have this dipole transition rule that the angular quantum number delta L can only change by plus or minus 1. That is why, for example, you can have in this case S to only P transition. That's also why you're probing the partial density of states, unlike photoelectron spectroscopy, which probes the total density of states. So what I have not told you is the other aspect. Why do these calculations look so different, although they are for the same material, gamma germanium nitride? They look so different because this is a ground state calculation, the right one. This means in the final state of the emission process, you have a ground state with 2 electrons in the 1s shell completely filled of nitrogen. In the final state of the absorption process, there's the effect of the hole, which disturbs and perturbs strongly the band structure. So the difference between the blue and the red calculation is left side excited calculation, not a ground state calculation, right side ground state calculation. Now let's talk about the solution. How did we come up with measuring the 5D energy position? And this is for people who are new to these techniques. Now, the next two slides are a little bit more complicated, because what you need to now distinguish is, everybody knows in absorption spectroscopy, the incoming photon energy, but now there is another parameter. What is shown here on the right side are for 3 different samples in different colors. It shall not matter for the moment what these are. They are all nitrides. I have the slides for what these samples exactly are, but I want to focus on the science. So we have 3 different nitride samples. These are the absorption spectra. And then what you're not so familiar with, these are here what's called resonant emission spectra. So always grouped in color for 2 different excitation energies for the same sample in the same color. So you have 2 different excitation energies. And now the new thing is, you now need to always distinguish the incoming energy that we use for absorption on the right side, and the emitted energy, which is on the left side. This is now here, the axis is the emitted photon energy. So this would be the emission spectra. In other words, as I just pointed out, the valence band. And now these 2 gray lines show you the excitation energies in the absorption. Where do we tune our excitation energies to measure the corresponding 2 for 2 different excitation energies, these 2, and where do we measure our emission spectra? So what we want to do now, and this is where I usually lose a little bit attention in the audience. So what we want to do now, we want to zoom in on only this bluish grayed out area. So we zoom in, and then we need to do, unfortunately, one other thing. We need to not display the energy of the emission energy here. We need to display the energy loss scale. So what that means is we take each of these spectra and subtract the excitation energy from it. What this means is that the excitation energy, of course, which is the elastic peak, the incoming energy, that ends up at 0. Why? Because we just subtract the incoming energy. So these peaks here, the elastic peaks, the incoming energy, end up to be at 0. And then we have the energy loss scale. This is what you do when you when you are after energy loss feature. So this is what I'm going to show on the next slide. Very different visual impression, just the same spectra shown here, just on a different energy scale, loss features, and scaled in height. And this is what's shown here on the right side. So the first thing to realize before you get upset about that, this looks like, as I always jokingly say, like a subatomic physics experiment, because it has very strong or large statistics. That is because these photon experiments are extremely photon hungry. If you go back, where do we excite? We excite actually before the absorption even kicks in. So this is basically the least likely way of having photons absorbed. That's the first problem. The next problem is, so it's a very low cross section. The next problem is europium, which we are after, is unfortunately only 1% typically concentration in the dopant, as the dopant. So this is 2 effects that make this extremely photon hungry. So that is why we have now taken fits, and we have always fit. The elastic peak is in red, the blue is the spectrum, and then we have now what's called an energy loss feature, which are these broad sign features. Okay, it shouldn't bother us for the moment that we have 2 different excitation energies. This is a little bit too detailed, but I can explain it if you want to know. So the first thing I would like to note is we have here in the bottom, the SLA is without doping, and the SLA, this spectrum here with europium, is the doped sample. So when you compare doped and undoped sample, although very statistically noisy, we say that there is no loss feature in the undoped sample here. And that tells us that this feature, whatever the energy loss is, it has to do with europium with the dopant. So now the question is, what you see here always, you take this to be at 0, and then there's something like a half or 0.3 eV, there are these losses. So what happens is you have photons coming in, you have photons coming out. These photons have a reduced energy by about 0.3 to 0.5 eV. Now, the obvious question is, what is this due to? So that's what we are after. So the first thing is we assigned this first intuitively, we assigned this process due to the loss feature due to europium. What is the process? So then what we did, so what you see here, the sigma only fitting parameters. So you see here for the 3 different samples in red, the 3 energy loss features for different host lattices. Again, we have different energy losses of 0.2, 0.37, and 0.46. These are the loss features, the energy losses in our resonant inelastic X-ray scattering spectra. Now, what we do is we compare these values with the quenching data. Quenching, here again, we show the thermal quenching. This was due to promotion of 5D electrons through thermal excitation to the conduction band, and therefore reduction in luminescence. So these values with an error bar, and they, of course, of lesser quality or relatively poor statistics, agree, which led us to assign these loss features to indeed the energy loss feature is due to the promotion of a europium 5D electron to the conduction band. So this is exactly what I promised originally. So with this technique, we found a way of determining the position of the 5D electrons with respect of 5D orbital with respect to the conduction band. Yeah, I think the rest we can ask upon questions. I wanted to focus on so this is the key outcome. We found a different alternative way that is independent because it's a RIC spectrum, it's independent of the impurity concentrations. We found another way of determining the position of the 5D with respect to the conduction band. Now, what I wanted to quickly show you, which I thought always was very interesting. So here we have now 3 different materials in 3 different colors, and these tall peaks here normalized to the height. These are the, of course, you notice the energy range in the visible. These are the visible photons that you use in the LED. Okay, so you can see for different hosts, it's always the same transition, europium 2+, 5D24F. The wavelengths are different because we have tuned different, or we have involved different host lattices, although I didn't really reveal what the exact host lattices are. So the point is now that what I found very interesting, when you compare the blue spectrum, the undoped sample that has no emitter in it, you see actually what you would occasionally expect. You see the conduction band to valence band transition. And then the interesting part is, there's also another one on one sample here, the 4F to a 4F7 to a ligand hole transition B that shouldn't bother us. But what you see is, as soon as you dope it and you go from the same sample, SLA, from the blue spectrum, undoped, to red, doped, then this basically becomes dead flat, and all the energy is channeled, or all the decays are channeled toward the channel that you want, the visible emission channel 5D24F. So this was quite instructive to see this in this way. So to put this part, so to speak, to rest, I wanted to quickly show you what we have then finally accomplished is that for 3 different materials, so here's always the short form, here's the exact long form. For these 4 different materials, we have always the same dopant and a different lattice. And we have determined now all the pertinent energies. So from our RICS data, we have determined here always the 5D to conduction band. Then, of course, from our luminescence with the optical spectrometer, we know the 5D24F. And then we also know, of course, the conduction band from XAS, which we probe. We know the valence band from X-ray emission. And we even know from Zeol also the 4F and 4F6 level. So bottom line is, what you need to know for this kind of research, where do all these orbitals lie? And this is what we managed to do. I wanted to show you because people have occasionally asked, well, these are quite strange fits, and are you sure that this is really true, basically? And what we have done now with the improvement of our beamline, thanks to TEAC, we show here another material. Here you can see with your bare eye, for this is an oxygen material, you can see the loss feature. And although there is a fit in there, you don't really need the fit. You could see this with your bare eye. So it's this gave us great relief in terms of, is it really true that these that we can use these fits always to do that? And you need, of course, a top-notch synchrotron to perform these measurements. So this was only to put your mind at ease with that these otherwise poor fits. Now I wanted to spend 5 minutes on one other interesting problem, and that sharpens your senses a little bit about luminescence materials. So again, you have seen this graph a moment ago. These three features here are again the 5D24F emission lines, very narrow, are tunable through the choice of host lattice. That's all really great. And now what I want to, of course, ideally do, or we want to do, we want to also calculate these. Now, the problem is we are only interested in these peaks, and anybody who has ever tried to do a calculation, this is what we essentially want to do. We have one peak measured is the black curve, and we have one calculation. The problem is that the absolute height of the peak, in other words, the number of outgoing photons, is nothing you can ever really correlate with your in absolute numbers with your experiment. There's always a proportionality factor because you can neither measure nor calculate absolute photons. So that should be clear. Anybody who's ever done a spectroscopy experiment, the height is always scalable. There's always a proportionality factor between the two, experiment and calculation. Now, the next thing is the energy or the wavelength of this. So this is, of course, visible light here now. So the problem, anybody who's ever also done a DFT calculation knows that it is not possible, especially in the visible range, with great certainty to predict the exact emission wavelength. In other words, you generate in a calculation a Gaussian peak where the height is relatively random and the position is, well, somewhat random. Of course, it has some meaning, the energy, but it would not be suitable to do predictions where the energy exactly lies. So the funny problem, and then there's one more parameter, the width of the line, but then you are basically given to have one Gaussian curve roughly, and you want to you can shift it anywhere and you scale it in height. So this is not a good experiment where you want to extract a lot of information from to compare to a calculation. And why is this? This is an interesting aspect, and it always is surprising to me when you go to conference about luminescence. There's, of course, a lot of different transitions. So let us look here. This is a table of the lanthanides. Unfortunately, I have now only been able to track down one for lanthanum 3+. So that is why we are looking at europium 2+. And because this table or this graph that I found is for 3+, this is actually europium here then. Okay, so only one difference in Z. The point is now, where do the 5D orbitals reside? And I show this here in gadolinium and in europium 2+, they reside here. That is the reason when you populate 5D and it decays, it can only decay to the ground state. So I would go out on a limb and say the really only relevant today with modern LEDs, relevant materials are two elements, europium 2+ and cerium 3+. The reason is only there do you get clear emission from 5D to 4F. Here, or for example, let's look at samarium. Here you would have actually a decay from wherever the 5D lies. It would decay into all these other 4F states and would not be a pure spectrum, would have a lot of different wavelengths. So this is not what you want. You want to have a tunable. Of course, so this is the reason on one hand is a problem. On one hand, what we want is we want to have direct transitions from the 5D with only the ground state in between. This is great. So only in cerium, this would be also the case. But on the other hand, it creates then, of course, only a single one band spectrum like shown here, and that is difficult to calculate. So what is our solution to that? Our solution is now we look at what's called excitation spectra. So we don't look at the one single spectrum or feature here of the 5D decaying to the ground state, we are looking now at excitation spectra. So when you take, for example, here, the ground state electron, you can now probe, of course, the 5D, but you can probe also all the other 4F levels. And that is what is shown here. This is called an excitation spectrum. So the point is, so this is now praseodymium 3+ is only something we found. And then there was a calculation for praseodymium 3+. You can calculate this. The point is, the single point is this: the 5D always, 5D to 4F are single peak, and we need more spectral information that unfortunately in europium 2+ and technologically important materials cannot have, because the point of these materials is pure transition to only the ground state. So what we do is we now measure the optical excitation spectra, then try to calculate these, and then hope that the set of parameters that we used to determine the system and that allows us to calculate good excitation spectra, that parameter set will hold, and then will allow us to also predict these spectra a priori. That means before you do the calculation. So that is, so to speak, the holy grail, and Tristan is working on this. So what we have seen here, these are half-year-old results. So these are for a different sample which we found online, cesium, magnesium, triple bromide, they dope with europium. These are the measured excitation spectra. And then there is a calculation by another person, the paper is given here. And Tristan is working now on getting ADF, this code running to produce these excitation spectra. And hopefully from that, we will also be able then to calculate the emission. Now I want to make a complete switch in gear. Oh, I wanted to first thank Inspire. So here you see my group as of last year when we had a little pizza party at my place. Tristan is the postdoc. Cody was a summer student. Mernaz is a PhD student, and so is Peter. And these people have name tags not because they are especially important, but because they are all funded by Inspire. So they, this is of course a great source of funding and a great program put together like these talks, hopefully today, and we very much all appreciate this. So why I also have this, I haven't mentioned Cody earlier. Cody and Tristan are the two people who did the research on the next on the next system, germanium phosphor 2 nitride 4. So there was, of course, it's a nitride. So the idea is that our collaborators work on finding other possible host lattices for LEDs. But this was a new material at the time. So this was the first material of this class. M stands now for any kind of material. Calcium, strontium, barium, these materials have been realized in this class of M, P, 2, and 4 of phosphonitrido or nitridophosphates, they are called. And so this was the first time that this was realized with germanium. Again, what is typical in these structures is that you have these tetragonal corner sharing nitrogen sitting on the corners. And then in this case, there is always one element inside here, the phosphor. And the first interesting thing was that when you look at the bonding scenario, these are from Cody and Tristan, some electron density plots, then it turns out that there are these P and 4 tetrahedra that you see here, and germanium only forms bonds to there are 4 non-equivalent sides, and 1, 2, and 2, and 4, and germanium only bonds and shares electron density with 3 of those. So there is no shared electron density with N3, as you can see here, germanium 2 and 3. So that was the first surprise that makes this somewhat unique. And the next surprise was, which I show you here, that this was a nice demonstration of the relevance of lone pairs for the structure of this material, and what also the lone pairs have a real impact into the structure. So what are lone pairs? You may know, or I think you will know, that there are valence electrons. Those are the electrons that typically participate in the bonding, most typical covalent bonding. So these are all the, I would call it laxly outer electrons. And not all of them necessarily have to participate in bonding. And those that are not participating in bonding are referred to as lone pairs. And to the best of my knowledge, so this was the first time where we have seen them so clearly. Here you see the electron density plot. Here you see the germanium, and the two arrows now point clearly to the lone pair. What was also interesting, it has been in soft X-ray spectroscopy always a little bit challenging to measure phosphor L23, so 2p whole 2p emission for phosphor. So we did this at the Reichs beamline, and here's of course the phosphor absorption spectrum. And here we have, because it's germanium phosphor nitride, we have also the nitrogen edges, so the nitrogen K edge. So here you see the emission from in filling the 2p hole in phosphor, and here you see the emission of filling the nitrogen K edge 1s hole in nitrogen. And then, of course, we can always determine also the band gap. So the interesting part was germanium was present as 2+, and what makes these materials stand out from all these other materials that have been synthesized as phosphor nitridophosphates is the presence of the lone pair. But it didn't stop quite there, because we were surprised. Remember, I just showed you the band gap. We don't dwell on now too much time here on exactly what the energy is, but bottom line is wideband semiconductor is what I would refer to. Maybe some people would even call it an insulator, depending on at the two edges, what the band gap is. So clearly there should be no visible luminescence, because the band gap is just too large. When you have an electron crossing 4.2 to 4.6 electron volts, this would be in the ultraviolet. To our surprise, we always do that because TEAC implemented a nifty optical spectrometer. We can measure also what's called X-ray excited optical luminescence. So we excite now with 500 electron volt soft X-rays, making sure that we are above the nitrogen edge to have efficiently depositing energy. And then we see this black spectrum, the emission. It's called actually luminescence because it's in the visible. And we didn't expect that, and according to our theory, in quotation marks, it couldn't be present. It turns out, and this is something that Tristan has somewhat pioneered this method, we now can do in our calculations, we can take out, for example, nitrogen or germanium atoms, so we create defects. And it turns out, and he has done this here on the right side in the calculation, you see here there are 1, 2, 3, 4 non-equivalent nitrogen sites. He has taken in subsequent calculations always one of those sites out, and this gives rise to the spectra. The point is, I summarize it, the point is when you take out a nitrogen atom in GE, P2, and 4, it turns out that all these additional states here in the band gap shape up. When you look at the germanium, here we have calculated the same thing. When you take out a germanium atom, then the band edges are reshaped here. It's the red curve, but there are no additional states in the band gap. So the upshot of all of this is, with the help of our calculations, we then be able to assign, here is now the fits, we will be able to, or we were able to assign that this luminescence comes from intra-gap defect states. So you take out you create a certain imperfection, and that leads to additional electronic states in the band gap. And this now gives rise to visible luminescence that would be otherwise not expected in a perfect crystal. Okay, this leads me to my summary. And so I've shown you that when we're exciting at the conduction band edge, we see energy losses, and we ascribe or assign those or attribute those to the energy loss when a 5d electron is promoted to the conduction band. And the nifty thing is, because this is done with RIGS, the inelastic scattering method, this is not important or affected by defects. With an error, these 5D conduction band energies also line up or align with our thermal quenching methods. And then together with all the other energy levels, it is important that these techniques allow to completely determine all the energy levels. So what I wanted to quickly say as an absolute last thing is that what is not so obvious, and there are still people at CLS, I know that question what the value of Xeol is, because the obvious strange thing is that you go with your outcoming energy, luminescence, in the visible. Why would you go so far away from it with your excitation energy? This is the unique thing. And let me say in one sentence, why is it still advantageous? When you have a complicated system like DNA, for example, and you measure a visible luminescence in DNA, with all these atoms and elements in there, it will be nearly impossible to determine where this comes from, the luminescence. What is, though, good about our techniques, exciting in the soft X-rays, we know exactly where we excite. So we always excite in the beginning, say in nitrogen 1s, to the conduction band, and then we see how the decay unravels from that. So there are benefits to these techniques. Thank you very much.
Thank you, Alex. That was really interesting. I'm definitely gonna have to do more reading on this. So now we've got about 10 minutes for Q&A. So if you are shy and don't want to ask the question yourself, feel free to put it in the chat and I can read it out for you. If you want to ask the question yourself, there's that raise your hand feature in Zoom. So feel free to ask questions.
Great. So I don't have to monitor this. You do this, right?
I will monitor for you, so you don't have to worry about that.
Yeah, great.
So while people are thinking up questions, we do have a two-part question from Artelin. First, have you considered using germanium or phosphorus NMR to probe the chemical environment in these compounds?
No, the reason is twofold. The first thing is, as you note, first of all, this is NMR is a relatively, well, difficult technique compared to the time it takes, not the calculation, but the measurement. So, but as all techniques, it always will provide additional information. So in that sense, I'm in favor, in principle, of doing that. So far, we have not done this because we couldn't expand on that. We might do it because it's available at certain places, so we can even send in a sample. So the one thing why this would be a good idea is, it turns out, you might ask, you have three elements, germanium, phosphor, and nitrogen. Why do you probe only phosphor and nitrogen? Why not germanium? Yeah, and the point is that germanium is, for reasons that I can get into, but don't have to, is basically not possible to probe in the energy range that we have access to. That has to do with, it's basically the lightest element. When you look at these curves in the X-ray data booklet where they show you the fluorescence yield, germanium is basically the first element that has the lowest fluorescence that you would see. So it is not enough. Although when you go one element above it, silicon, then we measure a lot of silicon. But in germanium, that's not possible. So that's the reason, in case somebody has a question, why we didn't measure germanium.
Interesting. Thank you. And then the second, there was a follow-up question for that. Are there any contributions from germanium d orbitals?
Now the question is, what does contributions mean? So, I mean, the d orbitals are bonded by, I have to look it up, by probably 25, roughly, I'm guessing, 25 electron volts. So they are not valence electrons. So, and therefore, when you mean bonding, contributions to bonding, they are not important. Of course, what we wanted to do is, and we've tried this, we wanted to see also create other holes and then see the germanium emission. But this was, for various reasons, I don't go into detail, was again not possible. So have they contributed? I would say is a no in terms of the experiment and in terms of the bonding.
Okay, thank you. I have a series of more questions in chat. I'm just going to check if anyone has their hand up. Nope. Okay. So I have one from Rhiannon. She says, great talk. I may have missed it. Did you keep the organic environment of the europium the same across your different crystal lattices? And then I'll let you answer that first, and then I'll answer the second part or ask the second part.
Okay, the organic environment. So first of all, the short answer is, did I keep it the same? Yes. I mean, that it would only change when you either change the matrix. Of course, we have 4 different samples. Therefore, it has changed between samples. But did I keep it the same? There are no aging processes or oxidation or anything like that that would affect it. So I would say it's fair to say, yes, we kept it the same. It will switch when you switch between different lattices.
The second part to that question, would you expect that changing the antenna would change the transition energies measured?
Changing what?
The antenna.
Antenna?
Rhiannon may need to clarify. Okay, we'll come back to that question.
Okay.
I'll give her time to type. Oh, she says here the antenna ligand on the europium, assuming you used one.
So then read the question again. Now, the europium is not the ligand, but what about the did I consider changing what?
Okay, so the additional question was, did you keep the organic environment of the europium the same across your different crystal lattices? Yeah. Would you expect changing the antenna would change the transition energies measured? And by this, she's referring to the antenna ligand on the europium, if you used one. Yeah, when I changed the ligands, that is, I had the slide. I don't want to go back to it for the sake of time, but when you go back to the slide, since it's recorded, which showed the nifoglosetic effect and the crystal field splitting. So you had this graph where the crystal field splitting clearly affects the larger the splitting, there's a redshift, and the visible spectrum will be shifted. So yes, it would change once I make fine tuning to the crystal host lattice. Okay. Yeah, she said sorry for the misunderstanding that she clarified. So Yasemin has a question that is not really related to spectroscopy, but what is the difference between scintillator process used in X-ray detectors and what I assume is the scintillators used in infrared region detectors?
The scintillator, I mean, this is basically luminescence, of course. With scintillators, you go usually, that refers to other impact of not necessarily visible photons or soft X-rays. It refers to, say, particles or cosmic rays or something like this. So that is what scintillators is. Now, the other part of the question is, I mean, the obvious thing is when you go from infrared to other energy ranges, I don't quite understand it. There's fundamentally different processes involved when you have different scintillators. Some give off signals in the infrared and some give off signals in other energy ranges, from visible to UV to whatever. So I don't understand what the question means. What are the differences? The main difference is you use them for different things, because scintillators are not necessarily used for impact of photons. You have photon detectors, but impact of particles, my understanding. And the other thing is, of course, when the wavelength range changes of the outgoing radiation, then also the underlying processes typically change.
Does that answer your question, Yasemin? Okay, I'll give her a moment to reply if she's going to be typing that out. Are there any questions from anyone else in the audience that they want to ask in person, if they don't want to put it in chat? Feel free to put your hand up or say something. Okay.
In the meantime, maybe I can summarize one thing. So what I would call always the holy grail, of course, we are years away from it. The first thing is you want to understand, how does a different host lattice or crystal, how does it affect the luminescence properties? That is something you want to get away now, ideally, from always like a druid in the Middle Ages, change your systems and then see what the effects are. Same with superconductivity. Ideally, you want to predict it in advance. So you want to basically design a material on your computer and then predict what the luminescence is and say to people, hey, this is what you should synthesize in order to have this or that parameter in output. Yeah. So, and of course, the calculations are difficult. because very involved, because of large matrices involved. So this is what makes this difficult, and that's what we are also working on. So ideally, hopefully before my retirement, we will get to the stage where we can, on 1 or 2 samples, predict what the luminescence properties will be, and then likely be proven wrong in the experiment.
We'll keep our fingers crossed.
Yeah.
Okay, last chance for questions, although I suspect since we're getting close to the end of our session, we should wrap things up. Thank you again, Alex. That was a very interesting talk.
Thank you for having me.
Yeah, thank you. So we will be having another seminar session in 2 weeks. So this will be April 5th at 1:30. And we will have Graham George up next. So thank you everyone for attending, and see you again in 2 weeks.
Bye-bye.